All right, back to x86 and its craziness. It is. So we talked about how we push on the stack, how variables go on the stack, how we can return from the stack, and we need to clean up the stack. I can't think of how else to say the word stack in the next sentence, but I'm sure I'll find another way.
You just did.
Stack, stack, stack. All right. Anyways, so now let's go ahead and try and bring it all together with this function over here. Look on the left, we have some nice C code where we have a sub, that stands for subroutine, that takes x and y, it multiplies x by 2, and then it adds y, and of course it returns the result. And then we have main, which looks like it takes an argument and the number of arguments. Okay, well that's odd. Well, we're not going to quite do that, so that's fine. And then return the subroutine on those components. All right, so real quickly, what I wanted to talk about is what r/m32 addressing is. That means that you can address a value from either a register or from a memory address. So the R is for register, the M's for memory. We're in 32-bit mode, so it's M32. So you can read that wall of text, but let's go look at the examples. Move just takes the contents of EBX, puts into EAX. Move, notice the brackets. It takes EBX, jump to the memory address that's stored in EBX, grab the value there, stuff it into EAX. Down here, take EBX, add ECX times some x value, which is a constant, basically calculate the memory address with this formula, then go to that memory address and then figure out, then get what's there and stuff it into EAX. Or you can have an even more complicated version of it if you are so inclined. Yeah. But x86 supports all of these. Of course, it does. All right, how should we pronounce that? Leah? 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 Lee? Lay? Lee? All right, load effective address. All right, let's see. Yes, pointer arithmetic. Do we get an example? Yeah, bless you. Uses the form, but is the exception to the rule that the square brackets means dereference value add. All right, you know what? Ignore this instruction, because this is only going to confuse you. Let's go to add and subtraction. Hey, wait, we've been doing these already. Look at the bottom. We have our stack pointer, and we add 8 to it. What does that do?
It adds 8 to the pointer value of ESP.
Does that increment or decrement the stack?
Increment.
Decrements.
No, decrement.
Right, because of course it's x86, so we're in backwards land. Of course.
Of course.
Of course. Hey, look at sub. Tell me, take a guess about what that instruction does down there.
It actually adds or increments.
Sub. It does add, correct. What is it adding?
It adds index.
What's that?
Negative.
Sure, it adds a negative. Of what?
In this case, CPH times 2.
Good start.
The memory.
It takes the value that's located at the memory address of EBX times 2. So it gets that value, runs 2's complement on it to complement it, and then adds it to EAX and then stores that result into EAX. Everybody got that? I'll say it again. First off, it takes the contents of EBX, multiply it by 2, jump to that memory location, grab the data at that memory location that I just calculated, then it runs 2's complement on it, adding it to EAX, takes the result of that and puts it inside of EAX.
Okay.
All right?
So
It's just subtracting EAX minus what's at that memory address.
got it. So it will put whatever the address is.
The data at that address.
Yeah. But it's actually adding it with itself, right? Or adding or subtracting itself with the operator.
EAX, right. So EAX is the one of the sources and it is the destination.
Is it the same thing for the add as well?
Yes, because an add There, you don't get multiple parameters, you just get 2. So,
Okay.
yeah.
Got it.
Ooh. What is that symbol?
If you wanted to add 2 different values together and then make it a different,
Oh wait, that's right. I can't see this.
That's
I know,
the,
right?
from what that table said, that's the modified value somehow?
I don't know what that symbol was. All right, how does this look?
It's a little cut off on the left, but otherwise fine. There it is.
Okay. So print an integer from storage and from a register. All right, so this is what we're going to ignore the C code for now. So again, extern printf, extender a to I. That means that these functions are going to exist external to our program and need to be linked in. Section data, this is where we store data. Hey, look, we're just storing a format, EAX equals %x, so it's going to be printing in hex, followed by a new line, followed by the null terminator, so that we know that the string ends. Have a text section. We have global main, which tells GCC where we are going to start our execution, and that main is, of course, down here. So let's look at sub, which is a subroutine or a function, depending on which definition you prefer. First thing, we push EBX, and we move EBX to the stack pointer. That way we preserve the old stack frame. And so we're getting EBP plus 8, so we're getting the first parameter sent to the function, and then 0C, which will be the second parameter sent to the function. And then, oh, there's the layout thing. Oh, well. We're going to do EAX times 2 plus ECX, and we're just going to calculate that address and shove it into EAX for us. And then since EAX is considered to be the return value of a function, we just pop EBT in order to restore the stack frame from the caller, and then we return. Okay. So what does main do? Well, let's see what it does. Set up the stack frame, push ECX. Oh, where did ECX come from? I believe, why are we pushing ECX? Who wrote this code? It wasn't me. Let's go see if it works if I delete that.
I'm not to blame.
Let's see. Okay, it still works. So we don't need to push EA. I don't know why that was there. All right.
Okay.
Oh wait, yeah, I do. Now I know why. We're pushing just to increment the stack pointer. That's actually the only purpose of that. Because then if you look at this, we get, was it 0C, and that'll be the first parameter. Then we're going to add 4 for some reason. That's a good question. Oh, I know why. Because that's argv sub 1. AKA, blah, blah, blah. Where are we? We're getting this thing, argv sub 1, so we have to add 4 to it. So in other words, this gets the pointer to argv, this jumps to the next element, the sub 1, then we push it onto the stack because we moved in ECX, we call A to I. We push twice up here, so we need to decrement twice, and then EAX has the result of A to I, so we need to store it. Then we need to, get the Y argument.
so like the 8 and the 4, are those like bits, like increments of bits or?
Yeah, so what's funny about this is we store it and then load it immediately. This code was definitely taken from a compiler that did not optimize anything as opposed to just doing it, because there's no point to this, but that's all right. Then we push the result, and then we're going to go ahead and push 1 to be x. So in this case, we are calling x to be 1, and we push it. Then we call sub, and then we decrement, we pop our stack twice, and now let's call printf. Well, we need to first push EAX, which was the result of our subroutine, push the format, which is the string constant up there in order to print it, call printf, and then pop the stack twice because we pushed it twice, and then exit cleanly. I'm sure you got all that perfectly. Right, Holland? All right. Why, oh why, was I told to do x86 in this class? All right. So, we call make. No, let's not call make. Let's get out of here. So, function args, we'll pass in 10, we get C. What happens when we pass in 11? Ooh, D. We'll pass in 20. Oh, 16. Wow, what's happening? Well, remember, that's the Y value. And what was the calculation for the Y value? Do we know? Does it tell me?
The Y value is.
Yeah, what we add. So it's plus 1.
And the X value that it took is.
1. Right. So we 20, 16, aka that's hex.
That is hex 22.
Hex 16 hex 20. 1 6. Yes.
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 So here's our X value. So let's go and change it to 2. So now if we run function, where is that? Hey, we have 1 8 because now it's 4 plus 20. Oh yeah, you're right, 22, yes. 4 plus 20, which should be 24. Because that 1 is a 16. 16 plus 8 is 24. Great, yay! Everyone got that?
Yep.
Good. And I think that's all we need to do for today. Yeah, so all this is confusing because these slides are actually really confusing. So we're going to start here. Stop here. So here are the instructions we know right now. No up, push, pop, call, red, move. You don't really need to know about the layout operation. And then add and subtraction. All right. That's great. Hopefully this makes more sense now. The first 2 instructions, push and move, they are actually setting up the stack. The next one, which is kind of a weird way to do it, is setting up hello world. Then it's calling printf. It's decrementing the stack by 4 because I guess, yeah, we just pushed once. All right. Oh, it gets the result and then pops again in order to exit the function. So hopefully this assembly is not confusing anymore.
So how do you know how much you need to decrement by for the stack? Like sometimes you do 4. Sometimes
Well, you pushed once,
Mm-hmm.
and that was it.
Okay.
So you pushed. We're on 32-bit. We pushed a 32-bit number, which is 4 bytes.
Okay.
So we need to pop off 4 bytes.
Okay. So that's the number of bytes. So is it normally 32?
We are writing 32-bit programs, so normally,
Okay.
yes.
So if we were writing
64-bit, it would be 8, yeah. And we're writing 16, it would be
in the other
2.
code, some of them were 8.
Because we pushed twice.
Oh, okay. So if you push twice, you can. Okay. I think I understand.
All right. Now that we all have that perfect. Oh, that looks cute.